So this is Leontief video 4, and the goal of this thing is some infinite series facts, specifically related to I minus m inverse. And we're looking at this both for economic reasons and also to just do some brief review related to linear algebra. So, first thing, recall from calculus, Calc 2 specifically. This is typically where this comes up. That if the absolute value of x is less than 1, then 1 over 1 minus x is this infinite series, or infinite sum if you prefer. And this comes from either geometric series, you can think about it, or Taylor expansions, or multiple ways to look at this. Right? So this can be rewritten as an exponent. That's a cube right there. And so we might say, like, well, you know, if x is a matrix, can we do a similar thing, right? So is there a similar fact about matrices? So it turns out we have the following. For a matrix M with I minus M invertible, we have I minus M inverse equal to 1 plus M squared plus M cubed if and only if the limit as n goes to infinity of m to the n plus 1 is 0. Now, this will mostly always happen, right? So basically what you want to get out of this, I will do a proof of this because it's not very long, but what you want to get out of this is under certain nice situations, you do have this equivalence. You do have I minus m inverse equal to the sum 1 plus m squared plus m cubed, right? So don't focus on the details too much other than say almost always this is the case. And this almost always happens when the entries in M are very small. And so we'll comment more on that in a second when we get through the proof. So the proof goes as follows. Is this equation, the one in blue, this can be written as if I minus m inverse is that sum, then I can write this. All right, those are equivalent. Right? So what we'll do next is I'm going to contract this into series notation, just because it makes it a little easier to work with. And then I'm going to turn it into a limit. Again, because it makes it easier to work with. So I'm just changing that sum to a limit. I can put the I minus m on the inside of the limit because it doesn't depend upon n. And then what I'll do is I'm going to multiply that I minus m inside the sum. Sorry, that's an n right there. And when we do that, we get m to the k minus m to the k plus 1. Now, if we rewrite this sum now back into a sum form, right, it telescopes, right, because this sum becomes m to the 0 minus m to the 1 plus m to the 1 minus m to the 2 plus m to the 2 minus m to the 3. This goes on plus or minus, and it ends at minus m to the n plus 1. That's just expanding that finite sum without the limit. Right? Now this contracts, this telescopes back in. Everything cancels except those two. Now, m to the 0, this is the identity matrix. And when we take the limit, the identity matrix doesn't matter anymore. We can pull it out of the limit, or you can sort of separate the limits like this. And then we can cancel the i's and move the limit to the other side. And that's the end of the proof. Now, it turns out that this will be true of almost all consumption matrices. And second of all, that this limit happens pretty quickly when the elements in M are pretty small, which means the inverse can be approximated, interestingly, by the infinite sum, by only doing a finite sum, but not very far. So let me just sort of make a comment to that effect. And then we'll look at what else this means in terms of the actual economy, because right now it's sort of maybe interesting mathematics, but it means something economically. So for 3, we'll say approximation use. So the approximation use is as follows, is that two things. For all realistic M, we do have this limit. And so we do have this equation. Sorry, it's a 1 minus m, I minus m. But moreover, what makes this sort of a bit more interesting is if the entries in M are pretty small, which they often are, then this thing that we're looking for, I minus M inverse, can be approximated by a finite sum. I plus M plus dot 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 plus M to the, say, T for some T. Now, I'm not suggesting that we know exactly how far we need to go to get a certain approximation. I'm just sort of saying that at some point we get something pretty close, right? So for example, if we have something like this. So I'm going to make this 4 by 4. If we have this one, this is not a particularly, these are not particularly small entries. Some of them are. This is just a 0. There are a bunch of zeros. It's fairly sparse. A sparse matrix has a lot of zeros in it. I have a bunch of zeros here that I don't really need to write at the end of the decimals. That's okay. So it turns out that in this case, this approximation, if we take this out, right, this is within 4 decimal digits to the actual I minus M inverse. Or within 4 decimal digits is, let me say it better, is identical to I minus M inverse up to 4 decimal digits. In other words, they're both approximately, I'm going to write equals. So it's approximately this. You pause and fill this in. So in other words, this is approximately this, and this is also approximately I minus M inverse. I'm saying equals because they're equal to that, to the fourth digit beyond the decimal point. If you could say they're approximately if you want to, but just to clarify that that's sort of where the approximations are the same. So what this means is like we can do these very short sums to get approximations for inverses. So we may or may not, I'm not saying this is computationally better, I'm just sort of pointing out this is an interesting side effect. The last thing we're really interested in is what this sum, again this thing back here, what this means economically, because it means something, right? This is really the reason we brought it up, is that something economic is going on here. So let me clear the screen off and then we'll do that separately. So 4 is economic meaning. So here's the deal. Suppose we take for granted, as is almost always the case, that these are the same. So if we go back to the Leontief output model, this is what we had in the original, like in the nice case. This is the case where I minus m is invertible, d is either 0 or non-zero, typically non-zero, and this is how we find Rp. This now becomes this. Which then we could expand to this. And you might wonder, like, well, who cares? Like, why is this relevant? How is this, let's say, interesting? And the fact of the matter is, it's very interesting. So here's the deal. Recall way back at the beginning that MP, what this was is this is the internal demand when P is produced. So what this means is that MD is the internal demand when D is produced. So let's go back to keep that in mind, but let's go back to sort of pretend we do nothing, right? And we say, hey, suppose we want to produce D. Right? So you say, like, well, let's produce D. And you go, well, maybe P is just D. And you go, well, but no, wait, like, if the production is going to be D, there's also some internal demand, right? So we say, but wait. When, let's say when the demand, or let's say when we produce D, we have internal demand MD as well. So then we go, okay, so maybe we should produce both. Like, that's the external demand, but then this is what must be produced internally. But then there's a problem, right? Because the internal demand MD means we have to produce that MD. And to produce that MD, what does that take? So here we have more internal demand, MD. This is the internal demand to produce the internal demand. This is as well. So then we go, oh, so maybe P is the external demand plus the internal demand for that, plus the internal demand for that internal demand. And you go, but wait, etc. So it turns out this goes on forever. So it turns out that at the end of the day, the production must satisfy not just the external demand, but the internal demand for the external demand, and the internal demand for that internal demand, and the internal demand for that internal demand, and on and on and on forever. And that is exactly what we had here. It's exactly this. So the reason this is sort of interesting is because basically we're saying we could have started from the other end. We could have started as an infinite series and worked back to I minus m inverse and done it that way. So it's just sort of showing that something that seems kind of esoteric, having this infinite series representing a matrix inverse, is actually economically meaningful when we look at the situation and what's going on. So that is the end of that video.